So you start to add some different elements of matrices that are brand new as far as conceptually that you've never dealt with before because they only apply to matrices. And so we're going to talk about a square matrix. We talked about a little bit. A square matrix is a matrix that has the same number of rows as the columns because it makes a square. That makes sense. And so just like in regular multiplication, you have a multiplicative identity matrix. A multiplicative identity matrix. This matrix, when multiplied by another matrix, doesn't change it. Just like the identity property. When you multiply by 1, it doesn't change the number. When you multiply by a multiplicative identity, the matrix actually stays the same. And just like with multiplication, you have a multiplicative inverse of a matrix. And when you multiply by the multiplicative inverse, you get the identity matrix, just like in multiplication. If I multiply 2 by its multiplicative inverse, which is 1/2, I will get the identity number, which is 1. All right, and that's the same, which is true for matrices. You have these matrices that represent identity matrices, and then you have matrices that represent inverse matrices. And inverse helps you because they help you solve problems. We've done solving with matrices, but we've never done it where you had to actually divide by a matrix. And you can't really divide by a matrix, but you can multiply by the multiplicative inverse, which is what division is. And so what we're about to find, help us find an inverse, which helps us then solve equations with matrices. So let's look at the next page where they talk about verifying that something is an inverse. All right. So the first thing is, are these inverses of each other? 2, 3, 1, 2, 2, -3, -1, 2. If it's a matrix that is an inverse of the other one, then when you multiply, you will get the identity matrix, which is just all ones in the diagonal from top left to bottom right. So if I were to multiply these and get an identity matrix, it would need to be a 2 by 2 identity. It would need to have ones in the diagonal and zeros everywhere else. And if that happens when we multiply, then that means they are inverses of each other. All right, and so we're going to do matrix multiplication here. We're going to take A, and we're going to take B, and we are going to see if they give us an inverse. Now first, can I multiply them? Well, yeah, if you have square matrices that are the same size, you can multiply them because your inner ones are going to be the same, 2 by 2, 2 by 2. So how do I multiply? What do I do to multiply inverses? We just took a quiz. Row by column. So I'm going to say 2 times 2 plus 3 times -1. Then I'm going to say 2 times -3 plus 3 times 2. Then 1 times 2, 2 times -1, then 1 times -3, and 2 times 2. Things are looking good. 4 plus -3 is 1, right? -6 and 6 is 0. -2 and 2, -3 and 4. So yes, these are inverses of each other. All right? If you multiply inverses, you will get the identity. It is true for all multiplication, right? If you multiply inverses just in numerically, you'll get 1. If you multiply inverses in matrices, you'll get the identity matrix. So go ahead and try to see if those are multiplicative inverses of each other. Just B. Just B. So this is a new term, determinant. A determinant is actually a number associated with the matrix. There's a pattern to solving for it. 2 by 2s are really simple. 3 by 3s are a little more difficult, but not really hard. And this is going to help us when we start to find inverses. So a determinant actually helps you find an inverse. And so the first thing you need to know is then how do I find a determinant of a matrix? For a 2 by 2, you actually do a multiplication with a subtraction. So what you do is you take the diagonal, the top left to the bottom right diagonal, and you multiply those. And then you subtract the product of the other diagonal. All right? And you'll see as they did it over here, AD minus BC. All right? Always subtraction, always the top left, bottom right diagonal, subtracting the other diagonal. So for this one right here, we would say -3 times -5. That's my first diagonal. Always subtract. And then 2 times 4. So what is -3 times -5? 15 minus 8. My determinant here is 7. That would be the determinant. Let's look at the next one. 2 times -2 minus 3 times negative 3. Negative 9. Pay attention to your positives and negatives. That will mess you up. So you have negative 4 minus the negative 5. What's my determinant? 5. And then the last one. A times A. A squared minus 0. So my determinant here is A squared. All right? Try those 3. A determinant. This is at the top of page 197. Top of page 197. So we've talked about verifying if something is an inverse. If you multiply inverses, then you will get the identity. We've talked about finding determinant, which is really simple. The biggest problem I have when people find determinants is they forget to subtract, or they mess up their positives, negatives when they do subtract. So now we're going to use the determinant to find an inverse, all right? And so there's a process that you do for this. You need to memorize the process, all right? You just need to memorize this procedure at the top here. The first thing they've given us is a matrix, the matrix A. First of all, your determinant cannot be 0. If your determinant is 0, then you do not have an inverse because you have to end up dividing by your determinant. And so if your determinant is 0, then you will have a problem. So the first thing is find your determinant. Make sure it's not 0. As long as it's not 0, you can go on with the next step. If the determinant is not 0, then the inverse. This is the notation for inverse. So pay attention to this. This is the notation for inverse. A to the negative 1 indicates you're finding the inverse. What you do is you take your determinant and you put 1 over the determinant. So if it's 2, you would put 1/2 here. All right, 1 over the determinant. And then you do this crazy switch with your numbers on the inside. All right? So if A, B, C, D was your original, A and D, they switched places. See this? A and D switched places. B and C just went to the opposite. They negated. If they were positive, they went to negative. If they're negative, they went to positive. All right? So you find your determinant, find the determinant, you put 1 over that, and then you do this on the inside. Switch your first diagonal, negate your second. And then you're going to multiply this guy through. So you're going to multiply it through. They just showed what this looks like. AD minus BC is your determinant. Okay, so they just showed it out here. These are the same things. But you're actually going to do scalar multiplication once you find this. You're going to distribute that fraction through to all of the numbers on the inside. Okay? And that will be your inverse, which means you could take this new guy that you find and you can multiply it by your original, and just like in the first example, you will get 1001. You will get your identity. All right? So let's do one. So the very first step in finding your inverse is to find your determinant. We want to find the determinant. All right, so find the determinant. Well, how do I do that? So I'm going to say negative 2 times negative 4, that's positive 8, minus 5 times 2, which is 10. All right, which is 10. So what is my determinant here? Negative 2. All right. My second step is to put 1 over my determinant. And then I'm going to multiply it by my switched. So I'm going to say switch these guys, negate these guys. All right, so that's what I'm going to do. 1 over negative 2. And then I'm going to switch this column, right, this diagonal rather. So I'm going to have a negative 4 here and a negative 2 there. I'm just switching them. And then I am just going to negate this one. So I'm going to change the positive 2 to negative 2, the positive 5 to negative 5. All right? And then my last step here is to do scalar multiplication. So scalar multiplication and simplify if you can. Simplify if you can. So I'm just going to distribute that negative 1/2 through. So negative 1/2 times negative 4 is what? Positive 2. Negative 1/2 times negative 2 is positive 1, right? Negative 1/2 times negative 5 is Positive 5 halves, yeah, or 2.5. And then negative 1 half times negative 2 again is 1. This is my inverse. So if my original matrices was an m, this would be m to the negative 1, or the inverse. All right. For this one, I'm going to find my determinant. 3 times 6 is 2 times 9 is, so no inverse. You would say no inverse here. Does not exist. The reason it does not exist is because I cannot have 1 over 0. That does not work. So then, to solve this equation, let's say I just gave you an equation like this, like 3 times x equals 6. What would you do to solve? Divide by 3. Another way to say divide is to multiply by the inverse, right? Correct? And so if I were to give you then this matrix equation here, what would you say to do here to solve for that x? Divide or multiply by the inverse. So then if I need to solve this guy, I need to find the inverse first, okay? I need to find the inverse first. And I will say that order matters here. So when you do this process, you have to actually multiply in a specific order, all right? You have to multiply in a specific order. Whereas over here, order doesn't matter. But with matrix multiplication, order actually does matter. And so whereas in normal numbers, I can say 6 times 1/3 or 1/3 times 6, it doesn't matter. In matrix multiplication, you always have to put the inverse first, okay? And so when you do it with matrix multiplication, order matters. So my first step then is to find the inverse of the one that is next to the variable, okay? I need this inverse because this is the one that I'm moving over, not this one. So my first step in solving the inverse then is to find the matrix. Negative 2 times 3 is negative 6, right? Minus 1 times negative 5, which is negative 5. So my determinant here is going to be what? Negative 6 plus 5, it's what? Negative 1. So they gave us a very easy inverse here. All right, then I'm going to put 1 over negative 1. What happens when I put 1 over negative 1? It's just negative 1. So I have negative 1 here. And then I do my switch. Negative 2 and 3 switch places. Negative 5 and 1 change signs. All right. And then distribute that negative 1 through. So I have negative 3, negative 5, positive 1, positive 2. That is my inverse, okay? That is my inverse. So if I were to multiply both sides by this, if I multiply this side by my inverse, I'm going to get the identity matrix. Well, the identity matrix times x is just going to give me x. So if I multiply this side by the inverse, I'm going to get rid of that matrix pretty much like I would with anything else if I multiply by an inverse. And I'm left with just the variable, the matrix x. On this side, I need to multiply these. Specifically, I need to multiply them inverse times the matrix that's left. So I'm going to take the inverse first, and I'm going to multiply it by the matrix over here, okay? All right, for starters, I can't multiply it the other way. Now, if I had a 2 by 2 on the other side, I actually could. But I can't multiply the other way because a 2 by 1 and a 2 by 2 won't multiply. So when it's like this, you can kind of see that's not going to work if I did it that way anyway. All right, now I'm just going to do my matrix multiplication. I'm going to do my row by my column. So I'm going to say this first row by the column, which is going to give me what? -3 times -2 is +6, plus -5 times 2, -10. Next row, I'm going to say 1 times -2 and 2 times 2. All right. And then my final step here is to add them. 6 and -10 give me -4, -2 and 4 give me 2. So the matrix that I was solving for is this. Now, just like any equation, you could go back here and plug it in. And you could do matrix multiplication and see that you would get this. And if you look in your book, you'll see they did the check. So checking it is like any equation. If I were to want to check this and I was going to get 2 here, I would say, oh, well, 3 times 2 equals 6. Yeah, that actually works. And you can do the same thing for matrix multiplication as well. You can plug it back in and solve. So I want you to try